In today's class and video, we are going to perform an experiment to determine the acid phosphatase activity. So let's start our introduction by looking at what an enzyme activity is. So enzyme activity is defined as the moles of substrate converted per unit time in an enzyme reaction. Its SI unit is kcal, and what you have to note is that 1 kcal is equal to 1 mole per second. And also a more practical and commonly used value is 1 enzyme unit, which is written as this and which is equal to 1 micromole per minute. So this is the unit that we are going to use for our calculation in this experiment. Now let's look at some factors affecting enzyme activity. So we have temperature, we have pH, we have enzyme concentration, and we also have substrate concentration. So these are few of the factors affecting enzyme activity. So let's look at materials and reagents that we need for this experiment. So the first is our artificial substrate, which is 2.5 millimolar p-nitrophenyl phosphate. We also have our acid phosphatase diluted in 1 in 10, 1 in 100, and 1 in 1000 dilution, and our 0.1 molar sodium hydroxide, water bath set at 37 degrees Celsius, spectrophotometer of wavelength 405 nanometer, our 0.15 molar EDTA in 0.01 molar citric acid buffer of pH 5.0, and p-nitrophenyl standard curve. So these are the various materials and reagents that we are going to use to carry out this experiment. So let's start. So the first step is the substrate buffer preparation. And to do this, we add 2 ml of the EDTA citrate buffer of pH 5.0 to 2 ml of our artificial substrate, which is 2.5 millimolar p-nitrophenyl phosphate of pH 4.8 in a test tube, and label it as A. So the next step is the dilution of our stock or crude enzyme. So also to do this, we dilute the stock acid phosphatase with distilled water in 1 in 10, 1 in 100, and 1 in 1000 dilution in a final volume of 5 ml, and label them as B1, B2, and B3 respectively. So this is how we can do the dilution. So to do 1 in 10 dilution, we pick 0.5 ml of our stock acid phosphatase and add to 4.5 ml of distilled water in a test tube. And also to prepare our 1 in 100 dilution, we pick from the 1 in 10 dilution 0.5 ml and add to 4.5 ml of distilled water. And also to prepare our 1 in 10 dilution, we pick 0.5 ml of our 1 in 100 dilution and add to 4.5 ml of distilled water. So when we are done, we label our 1 in 10 dilution as B1 and that of 1 in 100 as B2 and 1 in 1000 as B3 respectively. So the next step, or the third step, is the equilibration of our substrate buffer that we have prepared and our enzyme at 37 degrees Celsius for 5 minutes in a water bath. So as you can see, this is our enzyme, which is diluted. So this can be our 1 in 10 or 1 in 100 or 1 in 1000 dilution, and this is also our substrate buffer, which are being placed in a water bath set at 37 degrees Celsius to equilibrate them for 5 minutes. So the next is our substrate enzyme reaction. So to do this, we pick from tube B, so which happens to be our equilibrated enzyme, 1 ml, and add to our substrate buffer in test tube A. And what we also have to note is that this reaction mixture has to be kept in the water bath at 37 degrees Celsius. And another thing I also have to note is that obviously the total volume of our reaction mixture will be 5 ml because we added 1 ml of the calibrated enzyme to 4 ml of our substrate buffer. So the final volume of the reaction mixture is 5 ml. So the next is stopping enzyme activity with 0.1 molar sodium hydroxide at different times intervals. So we are going to use 0 minutes, 15 minutes, and 30 minutes. So the 0 minute will be used as our blank against the 15 minutes and the 30 minutes. So immediately, so that's at time 0. So after we've performed, or after we have prepared the reaction mixture at 0 minute, we transfer 0.5 ml of the reaction mixture to a different test tube containing 5.5 ml of 0.1 molar sodium hydroxide to stop the reaction. And we also have to know that we do same at 15 minutes and 30 minutes using our 0 time as our blank against the 15 minutes and the 30 minutes. Now, so as you can see over here, so this is our reaction mixture which is placed in a water bath at 37 degrees Celsius. So at 0 minute, we alicot, or we pick 0.5 ml of the reaction mixture and add to a different test tube containing 5.5 ml of 0.1 molar sodium hydroxide to stop the reaction. So don't forget the 0 minute will be used as blank. So also at 15 minutes, we do the same by picking 0.5 ml of the reaction mixture in the water bath and add it to a different test tube containing 5.5 ml of 0.1 molar sodium hydroxide to stop the reaction. And also at 30 minutes, we repeat the same thing by picking 0.5 ml of the reaction mixture and to 5.5 ml of 0.1 molar sodium hydroxide in a different test tube. So after this, we mix the components in each test tube wall and read the absorbance at 405 nanometer using a UV spectrophotometer as seen here. So let us look at the assumed table of results. So this is at 0 minutes. So as said earlier, so the 0 minute is we are going to use it as blank. And this happens to be the dilution. So this is the 1 in 10 dilution, and these are the absorbances over here at each time. And this is our 1 in 100 dilution with its respective absorbances. And this is also our 1 in 1000 dilution. So we can say at 0 minutes, so we are using the 0 minute as blank against the 15 minutes and the 30 minutes. So now let us look at the 15 minutes. So for 15 minutes, for the 1 in 10 dilution, our absorbance is 0.885. And for that of the 1 in 100 dilution, we had an absorbance of 0.146. And that of the 1 in 100 dilution, we had an absorbance value of 0.031. So at 30 minutes, for the 1 in 10 dilution, we had an absorbance of 1.112, and that of 1 in 100 dilution is 0.259, and that of the 1 in 1000 dilution is 0.041. So what we also have to note is that from this experiment, the 1 in 10 dilution absorbance value is the best to use as compared to the 1 in 100 and 1 in 1000 dilution. This is because the absorbance value for the 1 in 10 dilution falls within the absorbance range on the y-axis of our calibration curve. So we are going to use the calibration curve to determine the moles of p-nitrophenol hydrolyzed or produced in the test analysis from the p-nitrophenol calibration curve, as said earlier. So this is the calibration curve. So these are our absorbances plotted against the moles of the p-nitrophenol, and this happens to be the equation of the line for our calibration curve, which is y equals 6.7318s, and this is our r squared, giving us 0.9905. So now, using the equation of the line, which is giving us y equals 6.7318s from the calibration curve, and using our 1 in 10 dilution, so we note that from the equation of the line, our y is the absorbance value and the 6.7318 is the slope, and the s happens to be the moles of the p-nitrophenol hydrolyzed in the reaction. So let's see the moles of p-nitrophenol hydrolyzed or formed at 15 minutes and at 30 minutes using a calibration curve. So making S the subject, we can say that at 15 minutes, the moles of p-nitrophenol formed is 0.131 micromole, and at 30 minutes, the moles of p-nitrophenol formed is 0.165 micromole from the calibration curve using the equation of the line y equals 6.7318s. Now let's look at the calculation of the acid phosphatase activity. So first of all, we are going to calculate for the enzyme activity at 15 minutes and also at 30 minutes. So at 15 minutes, so our acid phosphatase activities expressed in micromole per minute will be given as the moles of p-nitrophenol extrapolated or determined from the calibration curve divided by the time. So if we are to do this calculation, we'll get 0.131 micromole divided by the 15 minutes. So we will get 0.0087 micromole per minute, and this happens to be the acid phosphatase activity at 15 minutes. Also at 30 minutes, we will have 0.165 micromole divided by the time, which is 30 minutes. And if you have to do this calculation, you'll get 0.0055 micromole per minute. And this also happens to be the enzyme activity for our acid phosphatase at 30 minutes.